Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good morning. It's my pleasure to introduce Ashwin Mahajala No, I'm mispronouncing that. What he said. He is a grad student of Johannes Görke at Cornell University, and he's been studying various forms of privacy, which he's going to talk about this morning.
Okay, my name is Ashwin Mahajala. I'm from Cornell University, and thanks for coming to the talk. So today I'm going to talk about, I'm going to try and excite you guys about research in data privacy, by describing some of the work that I have done in defining and enforcing privacy in data publishing over the last few years as part of my PhD. Okay, so why are we computer scientists interested in data privacy at all? The main reason is that we have identified that we can extract a wealth of information by sharing this personal information. So let me give you let's start off this talk with a couple of examples where this is actually true. The first example is that of data publishing. So traditionally, organizations like hospitals and the Census collect information from individuals and publish it in order to do research. So Census publishes information to do economic and demographic research. Hospitals publish information to study, say, how diseases spread or how you can categorize these diseases by age, gender, and so on. But however, much of this information is sensitive. Like, I don't want you to know what kind of diseases I have. So therefore, these organizations strive to publish this data in such a way that it discloses as much statistical information as possible while preserving the privacy of the individuals who contribute to the data. So the second scenario I'm going to talk about is that of the web. So traditionally, users have been like unidirectional consumers of this huge repository, but now with the emergence of the more colorful Web X.0 world, users are generating content onto the web at more rapid rates. So in a recent study, it was estimated that every day, apart from 8 to 10 gigabytes of public content that is being generated on the web in the form of like blogs and personal web pages, there's a whopping 4 terabytes of private content that is generated in the form of emails, instant messages, annotational metadata like tags and page views, social networks, and so on. So why are we interested in this private content? It's because such private content contains valuable clues into modeling user behavior and user taste, and we've already started creating web applications that exploit this user-generated private content in return for improved user experience on the web. Let me give you a couple of examples of such web applications. The first one is what I call social advertising. So traditionally, ads are placed for a user based on her browsing or shopping histories. But now that we have access to Alice social network, we can generate ads for Alice also based on the shopping histories of her friends, thus diversifying the ads Alice sees and potentially improving the revenue of the ad agency. However, we should be careful because Alice, for example, should not discover what Betty is shopping based on the ads that she sees. The second example is what I call user-targeted subscriptions. Surajit is not here, so let's pick a different example. Okay, Dan here is an expert database researcher, and Ashwin wants to read the papers similar to those that Dan reads. Of course, Dan is altruistic. He wants Ashwin to become an expert, but then he does not want Ashwin to know exactly what papers he reads, lest Ashwin know his diabolical research plans. Of course, there are enough of us in the audience who can create a simple application that can recommend papers to Ashwin based on the papers read by Dan and his collaborators and peers. But the challenge here is that Dan's privacy should be preserved. Right? So these three applications should have motivated to you that there's enough to gain by actually sharing this personal data. But in every one of these cases, there's a caveat that privacy should be preserved. So am I the only person who cares about privacy, or do people care about privacy in general? We don't need to go far to answer that question. AOL answered that question and found out the hard way that people do care about privacy. So what happened in August 2006? AOL altruistically released a list of 21 million web search queries in order to support information retrieval research. They anonymize the data by taking these user IDs and replacing them by unique random numbers. So now you don't know really who posed what kind of query. And they thought, cool, privacy is preserved, everything is hunky and dory. However, within a couple of hours of publishing this information, a couple of reporters from New York Times were able to uncover the identity of user number 4417749 based on the queries that she posed. And what's funny is not the kind of queries she posed or the fact that her identity was uncovered, but as soon as she was told that these are your queries and this is how we found your identity, she immediately discontinued her AOL subscription. So, okay, cool. People care about privacy. But what is privacy? I could give a whole 1-hour discourse on some philosophical, cultural, and social ramifications of privacy and the various definitions thereof. But for our purposes, I guess the best definition was given by Alan Westin, who defined privacy as our right to define for ourselves how, when, and to what extent you can disseminate information about ourselves to others. This is a very nice definition to start with. But unless we have a more quantifiable notion of what extent information is disclosed, we cannot clearly specify, we cannot clearly check whether some method for disseminating information breaches privacy or not. So therefore, in order to understand the privacy implications of sharing personal data, we need to answer two important questions. First, are there quantifiable notions of privacy that lead to simple enforceable conditions with using which you can check that an algorithm breaches privacy or not? And secondly, remember that the whole point of this exercise is to extract useful information from these privacy-preserving algorithms. So do algorithms that satisfy these privacy conditions, do they retain useful information about the personal data? So in this talk, I'm going to answer both these questions. In the first part of the talk, I'm going to describe how to formally reason about privacy, and I'm going to illustrate it using L-diversity, a condition for privacy that I invented in 2006. In the second part of the talk, I'm going to show you how a study wherein we took these formal privacy definitions and applied them to a real privacy-preserving application called OnTheMap that is hosted by the Census. I'm going to show you that useful information can be produced while provably guaranteeing privacy. I'm going to then conclude by showing you some of my applications of my work towards the grand challenge of building a privacy-aware web. So do you have any questions at this point of time? Good. Let's go on to the first part. So the first two parts of this talk are going to mainly focus on the data publishing application, and I'm going to talk about the web only in the last part. Okay, so recall the two main requirements of data publishing. First, you want to disclose as much statistical information as possible, and second, you want to protect the privacy of the individuals who contribute to the data. So since you want to disclose as much statistical information, ideally what you want to publish is microdata or unaggregated information. So this is an example wherein each individual is represented by a unique tuple, and which is cross-categorized by a large number of attributes. Some of these attributes, like name and social security number, are identifying attributes because they can uniquely identify individuals in the population. And disease is the sensitive information. This is the information that an individual wants to keep secret. Many cases, like in the AOL case, the only anonymization that is done is to remove these identifying attributes. Because recall, in order to guarantee privacy, you don't want to disclose what is the link between this sensitive information and the identity. And one way to remove it is to remove this identifying information. This was shown that you can easily get privacy breaches in 2002 by Professor Sweeney. What she did was she took supposedly anonymous medical data, which contained insurance records of like Massachusetts employees. And here again, name and social security were removed. And she joined it with the voter registration records of Massachusetts. She found out that the governor of Massachusetts was uniquely identified using the combination of zip code, birth date, and sex. So therefore, there's only going to be one record corresponding to the governor in both the voter registration records and the medical data, and she was able to easily link the name to the diagnosis and thus constitute a privacy breach. In fact, she found out that 87% of the US population can be uniquely identified using these three attributes. And such a combination of attributes that uniquely identify a large fraction of the population is called a quasi-identifier. So in order to guarantee privacy against such linking attacks, she proposed a technique called k-Anonymity. So k-Anonymity is a very simple technique which does the following. It takes these quasi-identifier attributes and coarses them such that every tuple in the table shares its quasi-identifier value with at least k minus one other tuples in the table. So for example, this table is 4 anonymous. Now, clearly you cannot identify any individual using the quasi-identifier attributes in the published table, and probably based on this, you might be guaranteeing privacy. So there is a nice quantifiable notion of privacy, and the computer scientists started a whole line of research trying to build efficient algorithms for k-anonymity and studying the complexity of k-anonymity and so on. Yes?
Is there an assumption that you know all the quasi-identifiers?
Yes, there's an assumption that you know all the quasi-identifiers. So what they do is they split the attributes as sensitive and non-sensitive, and they assume that these non-sensitive attributes are those that appear in public data. So they assume that the quasi-identifier is the whole combination of all attributes in the non-sensitive attributes. So this is the point of time when I started doing research in privacy. And rather than creating yet another cool algorithm for k-anonymity, I stepped back and asked the following question. So k-anonymity, as the name suggests, is a measure of anonymity. How does anonymity relate to privacy? Or more precisely, does k-anonymity guarantee privacy at all? And while asking this question, I saw some deep flaws with k-anonymity, and I'm going to show you two simple attacks that I can launch on k-anonymous datasets and breach privacy. So first, suppose that is the published table there, and I know that a friend of mine, Bob, who's a 35-year-old male from zip code 13053, has his information in this table. Now, given this information, I know that Bob's tuple corresponds to one of the last 4 tuples in the table. But even though I cannot uniquely identify his tuple, everybody who looks like Bob has cancer, therefore I know that Bob has cancer, thus breaching his privacy. I call this a homogeneity attack. Next, consider a friend of mine, Umeko, who's a 24-year-old Japanese in zip code 13068, who's also in this table. So again, like in the last case, I know that Umeko's tuple is one of the first 4 tuples in the table. However, unlike in the previous case, I still don't know whether Umeko has heart disease or the flu. But with some medical knowledge, I may know that Japanese have a very low incidence of heart disease due to their cuisine. And therefore, I can now deduce that Umeko has the flu with a very high probability, and thus breach her privacy again. So what did I show you? Initially, I showed you 2 privacy breaches, the Massachusetts governor privacy breach and the AOL privacy breach. And these were caused by re-identifying individuals in the table. Now, k-anonymity tried to patch this privacy breach by making sure that each individual is not unique anymore in the published data. But now I showed you 2 more privacy breaches where adversaries who had background knowledge could breach the privacy even without re-identifying the individuals in the table. So this whole methodology of first identifying a privacy breach and then creating an algorithm to patch that privacy breach and so on does not really work because one, data publishers do not know what are all the privacy breaches that are there. They don't know how to enumerate all of them. And even if you enumerate a list of them, they still don't know what other privacy breaches are possible. Right? So we need a more formal way to reason about privacy, wherein you first start off formally specifying a privacy model, then deriving conditions for privacy, and then designing an algorithm that satisfies these privacy conditions. I'm going to illustrate how one formally reasons about privacy in this model using L diversity, a privacy condition that I defined in order to overcome the shortcomings of k-anonymity. Okay? Do you have any questions at this point of time? Good. So before I go into this formal model and so on, let me give you a brief preview of what L diversity is, how it guards against the attacks that I showed you on k-anonymity, and then go on to describe this, how I formally derived L diversity. Okay? So recall that these are the attacks we showed on k-anonymity. One was the homogeneity attack and the other was the background knowledge attack. Now, there is no sanctity in this 4 anonymous table. There are many different ways in which I can anonymize it by coercing the 3 attributes in different ways. In fact, I'm just going to show you a different anonymized version of the table wherein I only split age into less than 40 and greater than 40 and so on, wherein each group of tuples which have the same quasi-identifier value have at least 3 distinct sensitive values, here heart, flu, and cancer, and they are of roughly equal proportions. So now, since there are 3 distinct sensitive values, clearly you cannot have a homogeneity attack because there are different values. And with one piece of knowledge, that is Umeko does not have a heart disease, you're only able to eliminate one disease there, and you still have 2 distinct values, and hence you still don't know what Umeko's disease is. So I call such a table a 3 diverse table. And in general, a table is L diverse if every group of tuples with the same quasi-identifier value have at least L distinct sensitive values of roughly equal proportions. And this simple sort of heuristic principle seems to guarantee the privacy that k-anonymity did not guarantee. Right?
Are your forcing operations predefined? I mean, are they...
You could either predefine them or you could do it however you want. For example, you can find what is the best coarsening of age and zip code and so on.
Yeah, but the zip code you're using 1306 star. So
Yes.
can I use 1 star 065 or something?
You could define whatever coarsening you want. I'm not pre-specific. At least for the purpose of this talk, I'm not really saying what are the pre-specified set of coarsenings that I'm using.
But then will the algorithms be?
That's a good question.
Their complexity will that?
Their complexity will increase. I'm not going to go into the complexity of algorithms based on the coarsenings, but there's a lot of work on what is the complexity of these algorithms based on what kinds of coarsenings you do. There are some algorithms which define predefined hierarchies. There are some algorithms which search for the best partitioning of your domain based on some heuristics.
And what's the relationship of the coarsening operations to the actual queries or the analysis that people do subsequently?
That's a very good question. So there's only maybe one or two pieces of work which actually look at. So ideally, what you should be doing is the following: you have a specification for privacy, and you have a specification for utility, which is say these are the queries I want, and I want to sort of get the best approximation of these queries. And then you take your algorithm, and you create an algorithm which satisfies this privacy condition and maximizes the amount of utility you want. That's how ideally algorithms should be done. There's only like one or two pieces of work which go towards it. I know that Professor Dan Sushi's student had a paper which sort of proves bounds on given a query workload, what is the how good does the algorithm approximate. But yeah, you have to base your algorithm based on the utility metric. I'm not going to go into that because it's mostly going to deal with the privacy aspect of it rather than the utility. You can put in whatever algorithm you want, but here I'm concerned with what definitions should this algorithm satisfy for privacy. Okay? Does that answer your question? Okay. Okay, so let's go on. So this is a nice heuristic principle which seems to guarantee privacy that k-Anonymity did not guarantee. But then we still can't answer the questions like what kind of adversarial attacks do we guard against? What is this L? How large should it be? And in order to answer those questions, let me go ahead and show you how we formally derived this condition. So how do you formally reason about privacy? The three steps are: first you formally specify a privacy model, then derive conditions for privacy, and then design algorithms that match these conditions. When I say formally specify a privacy model, you have to answer three questions. First, what is your sensitive information? What do you want to keep secret? Secondly, what is your adversary model? How much knowledge does the adversary have about the individuals who are in this table before you publish some anonymous version of the table? And finally, what is the mathematical model that describes when is privacy breaches and when privacy is not breached? Okay? In our case, these were the answers we came up with. First, what is this sensitive information? So privacy is breached intuitively by linking an identity of an individual to some sensitive value in the domain, right? So that's precisely what your sensitive information is, a link between the identity and one value in the sensitive attribute domain. For example, does Bob have cancer? Does Umeko have the flu? And so on. Next, what is the adversary model? So traditionally, in cryptography, adversaries are classified based on the amount of computational power they have. Here we assume adversaries have arbitrary computational power, but rather we distinguish adversaries based on the amount of prior knowledge they have about the individuals in the table before you publish any anonymous data. Here in specific, we look at limited kinds of adversaries who only know what are called negation statements. Of the form, Umeko, for example, does not have the heart disease. So that's one negation statement. Of course, if you have 10 diseases and you have 9 negation statements, you already know exactly what the disease is. So you have to sort of bound the number of negation statements an adversary has. So we bound it by what is called L-2 negation statements. I'll come back to what L-2 means in a few slides. Note that a data publisher may not know exactly what the adversary knows, because different adversaries may know different amounts of information, and even for a single adversary, he may know different amounts of information about different individuals in the table. So this is an important point that we will come to also in this talk. And finally, when is privacy breached? We say that privacy is breached if the probability of some sensitive predicate, given the published table and the adversarial knowledge, is very high. That is, if the adversary can link an identity to some attribute value with the probability greater than some threshold t, which is user specified, then we say that privacy is breached. Now note that this is not the only way in which you can define privacy. There are many different ways you can model adversaries. There are many different ways in which you can measure privacy and so on. I'll come to that point after I describe L diversity. Okay? Okay. So now I have this specification for L diversity. So in order to derive simple conditions to check for L diversity, we need to compute this probability. Right? What is this probability? This probability is basically the measure of uncertainty about the adversary has about which individual has which disease. And this can be easily captured in the random worlds framework, wherein you have initially, before the adversary has any knowledge, any one of the possible every world is a unique assignment of disease to individuals, and all of these worlds are sort of equally likely because adversary has no preference between these worlds, right? So now suppose I publish this table T star, which says that amongst the first 4 individuals, 2 of them have heart disease, 2 of them have flu, and all of the last 4 individuals have cancer. Some of these worlds become incompatible. For example, world 1 is incompatible because it has 4 cancer patients among the first 4 individuals. Next, suppose the adversary has a background knowledge in the form that Umeko does not have a heart disease. Then again, worlds 4 and 5 become incompatible because Umeko does have the heart disease there. So now by eliminating these worlds, we have now the set of all worlds which are consistent with B, the background knowledge, and T star, the published table. And now computing probabilities is very easy. For example, probability that Umeko has the flu, given the background knowledge in the published table, is the fraction of tables which are consistent with B and T star, where Umeko has the flu. And it's very easy to see that in this case, this probability will be equal to 1. So now I described to you a very simple way to compute these probabilities by counting these tables. But in general, counting this number of worlds which are consistent with B and T star is tedious, and in fact is intractable for more complex forms of B. So we'd like to know some sort of a representative theorem which maps this probability in terms of counting the number of worlds, maybe in terms of, say, the frequency of the sensitive values in the published table, right? And this is what is shown in our 2006 paper, which shows that in these kinds of publishing, the number of words that are consistent with the background knowledge in the published table, where, for example, Umeko has the flu, is proportional to the number of tuples in Umeko's group who have the flu. So given this proportionality result, we can easily find out what these probabilities are. I'm not going into the details. It's very simple. Okay, so what did I show you now? You know what the privacy model is. I showed you how to take this privacy model and compute what the probability that Bob has cancer, given some published table and the adversarial knowledge. And now, in order to guarantee privacy, all we have to do is check for every individual U and every disease S, whether the probability that U has disease S, given T star and the adversarial knowledge, is greater than the threshold, right? And if it is less than threshold for all U and S, we guarantee privacy. So are we done at this point of time? Unfortunately, no, because we don't know what the adversarial knowledge about U is. Because different adversaries have different amounts of knowledge, and an adversary may have different amounts of knowledge about different individuals. So therefore, we have to guard against unknown amounts of adversarial knowledge. And we do this in 2 steps. First, we limit the amount of adversarial knowledge about individuals. So we say that an adversary has at most L-2 negation statements. And then we consider the worst case amongst all these adversaries who have at most L-2 negation statements. Now, given these 2 conditions, we have 2 important properties for privacy. First, we need at least L sensitive values appearing in each group that share the same quasi-identifier value. Because if L equal to 5, an adversary can have 5 minus 2 is equal to 3 negation statements. And in this case, there is some adversary who knows that Bob, who's in this group, does not have heart disease, hepatitis, and jaundice. And therefore, he can easily deduce that Bob has cancer, right? Secondly, these L, even if you have L distinct sensitive values, they should be of roughly equal proportions. Because again, here you have 5 different diseases which are not of roughly equal proportions, and you already know that Bob has cancer with very high probability. You can actually make this condition very precise. In fact, for example, if T is equal to 0.75, then in order to guarantee privacy of the individuals in this group, we need that the frequency of cancer divided by the frequency of cancer plus the frequency of malaria is less than 0.75. We can actually come up with a very simple condition to check for privacy given the frequencies in a group. I'm not going into the arithmetic. It's very simple. Okay? Yes?
So it says, you say that I assume that he doesn't know that he doesn't have the 3 diseases.
Yes.
Do you make any, so he says I know it's either cancer or malaria. But he might, between those 2, one might have a higher probability.
Yes, so that's the kind of, I'm sorry? Yeah, so the question is this. So right now I'm only looking at adversaries who know that, say, L-2 diseases are not possible. However, there could be more other adversaries who may know that, okay, either cancer or malaria or hepatitis are possible, and these are the probabilities with which I think they are possible, right? So this sort of more probabilistic notion of.
Guarantee that cancer and malaria, all adversaries, between that they cannot distinguish.
Right now, the kind of adversaries I'm looking at, I look at adversaries who cannot distinguish between cancer and malaria, right? But you could think of adversaries who are more complex and have sort of these probabilistic notions of background knowledge. In this model, you cannot take care of it. But but you could come up with a model wherein you take that into account and then derive your probabilities. Yeah. One problem with that is the following. When you have this probabilistic piece of knowledge, you don't really know how to combine them. You may have to make some independence assumption, but the independence assumption may not be the right thing to do and so on. So it's a little complex. We tried doing it, but it's tricky. So we went with just the pure propositional form. Okay? Okay, so now I showed you, I gave you an idea of what L diversity is, how to derive it formally, right? But now we need algorithms that can actually create tables that are L diverse. So given this quotient table T star, it's very easy to check L diversity. Just go to every group and check the condition. However, finding an L diverse table is in general a hard problem because of the following reason. See, as Venki pointed out, there's not one way of really creating these coarsenings. In fact, there's a large number of coarsenings. Here I've showed you 3 different coarsenings of the quasi-identifier attribute, nationality, and zip. Moreover, this set of all possible coarsenings also has a nice structure in them. And there's a lattice structure wherein if you go up in the lattice, you strictly suppress more information. For example, here the top right table suppresses more information than the bottom right table, right? So now in general, this is a lattice search problem. Now you want to take this function of L diversity function, apply it to each point on the lattice and find which points on this lattice guarantee privacy. Even though in general lattice search is an NP-complete problem, if the function you're checking on the lattice is monotonic, then it's actually you have efficient algorithm, just like in frequent item set mining and so on, right? So we actually show the same monotonicity property, that is if T is a table that satisfies L diversity, by strictly suppressing more information, it still satisfies L diversity. And this is not a property that we generally have for privacy conditions. And this analogous monotonicity property has been exploited to build efficient algorithms for k-Anonymity. And all we do is we take these algorithms, and then we can now also check for L diversity, and we have an efficient algorithm for L diversity too. Yes?
The notion of L diversity also requires embedding the definition that all the different values have roughly the same counts.
Yeah, so I'm not going into the exact definition of what that is, but you're right, yes.
What I'm saying is that if you generalize something, can't you just, by generalizing that, bias the frequencies, and therefore now you're not L diverse anymore because suddenly cancer is 99% of the values in the generalized group? I don't know if I'm clear.
So, okay, the question is that, so L diversity requires that you have roughly equal, all the L different values are roughly equal proportions. Now your question is, when you generalize it, so when you take 2 groups, okay, and you combine them, that's what generalizing is doing, right? In fact, what happens is the operation sort of gets the distribution more towards a mean or a more average kind of a distribution rather than a more skewed distribution. So you'll never make cancer more skewed by doing this. So you cannot.
Why not? I mean,
because it's, so you suppose cancer is say 80% in one group and say 70% in another group. Yeah. Now by combining them, no matter no matter what the relative sizes of these groups are, it's a convex combination. So the percentage of cancer in this new group is going to be between 80 and 70. I can actually show you the math.
The implication of the analysis.
Right?
What is the implication of the analysis, right?
On the implication of the analysis is a good point. Your utility is going to degrade.
What? I mean, why is it useful? In that sense, every group is almost uniform. And any aggregation that I do out of these groups is actually going to increase uniformity.
Exactly.
In terms of the utility of this university, it's very less.
Exactly. So that's a very good point. And one way to control it is by saying that, okay, this threshold T is not equal to say half, it's slightly higher. So higher the threshold is, more skew is allowed in your groups. But you're very right. In fact, in any privacy preserving algorithm, the more privacy you want to guarantee, their utility is going to degrade more and more. And you have to find some point on this privacy utility trade-off which looks good for you. Yes?
small follow-up.
Yes?
I understand if you you have 70 and 80 convex
Exactly.
combination, you still get something between 70 and 80.
Yes.
However, each combination that you do might have cancer as the only common
Sure.
thing.
Sure.
And therefore, you have something that before it was 70 and not 70, but 30.
Yeah, right.
30,
So you could
have 30 and 1, 1, 1, 1, 1, 1, 1,
Yes.
1, 1.
Yes.
So
Yes.
you are violating the notion of all the groups having roughly the same number of.
No, it doesn't. I mean, that's what this proof of the theorem says actually. Even though the other diseases other than cancer are very different, you still don't violate that property. I mean, I'm not going into the details. I could go later on with you. Sure. Okay. Yes.
Can you guarantee that you can always find a data grouping method that always each group have some uniform distribution?
You cannot guarantee that. In fact, if your original table itself has a very skewed distribution, then even if you remove all the non-sensitive attributes, you still are going to have a very skewed distribution. So you cannot always guarantee, you're not always guaranteed to have an L-diverse table. You're right. So actually I'm going to show you some other things also wherein these kinds of problems are handled. Okay? Okay? Okay, so we have implemented this code and it's up on our website, and a lot of research groups have asked for it, including like places like World Bank and so on, because they think this kind of privacy is enough to guarantee privacy in their cases. Okay, so in summary, what did I show you? I started off with a description of a popular notion of privacy called k-Anonymity. I showed you some of the problems with that, and then showed you how to formally define privacy, and then derived formally this L-diversity principle that guarantees privacy. And then I showed you how it permits efficient practical anonymization algorithm. Yes?
All your algorithms, k-Anonymity, Untitled, they don't touch the sense. There is quasi-identifiers and less, right?
The kind of algorithms that I showed you right now, they don't touch the sensitive attribute. They only coarsen the. Huh? It's just historical reason. Yeah. I mean, what happens is in many cases you want to study the distribution of a sensitive attribute based on, say, age, gender, and so on, right? Now, if you coarsen your sensitive attribute, usually that's sort of a target attribute in your classification. Now, if you coarsen it, you get classifications on the target rather than the original domain. So you want to maintain the original domain, and that's why you don't coarsen it. But there are other algorithms where you may want to coarsen it. Yes?
And we have cases where you have multiple sensitive attributes and you want to.
Yes. So when you have multiple sensitive so the question is, what do you do when you have multiple sensitive attributes? Ideally, what you should do is you should take this multiple sensitive attributes and take the combined multi-attribute domain, and then look at privacy there. But still now your adversaries may have knowledge only with respect to single sensitive values, right? That, for example, Umeko does not have heart disease, and if the other attribute is, say, salary, then Umeko's salary is greater than 5,000 or 50,000 or something like that, right? So now there you have to be careful. When you define privacy, you have to, when you look at the privacy of, say, disease, you should take the salary as one of your quasi-identifier attributes. And you look at the privacy of salary, you have to use the disease as one of the quasi-identifier attributes, and then look at privacy. So that's how you should do it. Okay? Okay. So now one of the main contributions of L-diversity is not the L-diversity condition itself, but rather the fact that we now know how to sort of formally reason about privacy by specifying these three answers to these three questions. Okay? In fact, L-diversity has engendered a lot of other work wherein you get newer privacy definitions which span this whole space of privacy definitions. I'm going to show you some of the related work that L-diversity engendered. So first, remember, the sensitive information in L-diversity was just the link between the identity and the sensitive, some value in the domain, right? So I could have a three-diverse table wherein the three sensitive values are stomach ulcer, gastroenteritis, and dyspepsia. So now even though I sort of have three diversity, I still know that an individual in that group has a stomach-related disease, right? So you may want to guard against more complex forms of sensitive information, and that was done in a 2006 paper. Next, the background knowledge in L-diversity is very limited again. It's only information about a single individual. But in general, you could have more complex forms of background knowledge, wherein you want to say, for example, that if Umeko has the flu, then her spouse, Bob, also has the flu, and so on, right? So we looked at in a paper that I co-authored with others at Cornell, we looked at more complex forms of adversaries wherein background knowledge is captured in terms of a propositional formula over all the tuples in the table. And then we looked at limited forms of adversaries based on these more complex forms of background knowledge. There was other work from Wisconsin which looked at more other complex variants of background knowledge. And finally, remember the question wherein there are cases when the distribution of a sensitive attribute in the table is so skewed that no table satisfies L diversity. Now, one may say that a better way to define privacy is to look at, okay, what is the adversary's prior knowledge before looking at the table? For example, if I am publishing some cancer data set, and even without looking at the data in the cancer data set, I may know that an individual who's in the table has cancer with, say, 80%, right? So a better way to look at privacy may be a difference between this posterior probability that you get from the table and the adversary's prior probability. And this has been looked at by many different privacy conditions. One of them is T-closeness. One of them is Dan Sushu's D-gamma privacy, and so on. Yet another very strict privacy condition is called differential privacy. That was actually from Cynthia Dwork et al. From Microsoft Research. I'm going to talk about differential privacy in the next part of the talk, but that also can be phrased in this framework. So what I've shown you now is this whole space of privacy definitions. So what is the right privacy definition? In fact, there is no right privacy definition. Depending on your data and depending on your application, you have to come up with answers for these three questions that match your application domain, and then either choose one of these privacy definitions or create your own privacy definition for that application. I'm going to show you how one chooses a privacy definition in the next part of the talk. Okay? Any questions at this point? Good. Okay, so till now I gave you an idea of how one formally reasons about privacy, right? However, I did not talk about whether these privacy preserving algorithms preserve any utility. So rather than looking at L diversity and showing you some graphs with some existing small data sets, I'm going to show you a study wherein we collaborated with researchers in the Census, and we did a privacy analysis of a real census application. So the census application is called OnTheMap, wherein which synthetically creates data and publishes it for economics research. However, currently the privacy implications are very poorly understood, and that's the state of the art in most of the census applications right now. So we proposed the first formal privacy analysis of the application, and in doing so we met two challenges. The first challenge was a routine challenge, wherein we had this new statistical algorithm and a new application. We had to first choose a privacy definition and derive conditions when this algorithm is private. But more importantly, that this is where we should stop if our privacy research is actually mature enough. However, we found that none of the existing privacy notions have been tested with real data. And when we tested with real data, we found that in this case the data was very sparse, and there were no algorithms that could provide utility and guarantee privacy in the face of such data sparsity. So I'm going to show you some of the how we came up, what technical solutions we gave in both these cases. What is OnTheMap? It's this online application where you can go and say choose some location on the map. Say here I chose a location near Washington DC, and it plots where all workers who work in that location come from. So the workplace information, then they do this so that they can study like average commute distance and average employment and so on. Now, workplace information is public. You know where offices are, but you don't know where people reside, and this is something that you want to keep secret. So under the wraps, what's happening is each worker's origin, that is workplace, residence and destination of his workplace is represented using census blocks, where in each census block is like either 3 streets or a few blocks, few houses. And so if I know which census block you come from, I can actually stalk you. So now, in order to guarantee the privacy of individuals, the algorithm that is used is called Dirichlet resampling. So what they do is the following. They first, for each destination, they sample data independently. And for each destination, what they do is they look at the set of all workers and the frequencies of how many workers come from each block on the map. And then they add some set of fake workers to each block on the map, just to sort of hide the original distribution. And you have this noise-infused data. The only property that this noise has is that if there is some block that appears in the original data, some amount of noise is added. The next step, and I'm not going to go into the details of this, is called Dirichlet resampling. And the idea is you take this noise-infused data and resample synthetic data from there. The original algorithm creates Dirichlet models and samples multinomial probabilities, and I'm not going into the details of this. The only point I want to raise is that this is resampled in such a way that the synthetic data has statistics very close to the noise-infused data. Okay, but then I haven't told you how much noise I should add and to which blocks I should add the noise, right? Intuitively, more noise yields more privacy, but then we don't know the answer to these two questions. Even the census doesn't know the answers to these two questions, and right now what they do is they keep the total amount of noise a state secret. So in order to do better than security by obscurity, we looked at these two questions and answered it by doing a formal privacy analysis. So in order to do a formal privacy analysis, the first step is to choose a privacy definition. So in order to choose a privacy definition, you need to first formally specify what privacy is. So again, what is sensitive information? So here again, the sensitive information is a link between an individual and some residence block or some set of residence blocks on the map. Right? What kind of adversaries are you looking at? You consider an adversary, say Alice, who knows her coworker Bob has the longest commute amongst other workers in the workplace. And so now Alice can deduce that Bob comes from, say, some small set of blocks on the map. And Alice may also know that no other individual comes from that small set of blocks because everybody else has a shorter commute time. So these are the kinds of adversaries we're looking at. And when is privacy breached? Here we're going to use the notion that privacy is breached if the adversary's posterior probability is very close to the adversary's prior probability. Because if you have a workplace in Washington, D.C., then most people are anyway going to come from near Washington, D.C. And even without looking at the published table, I know that the probability that somebody comes from some block near Washington, D.C. is very high. Right? So given these three requirements, we found that the only current existing privacy definition that matched this specification was differential privacy. And differential privacy can be defined as follows. So in differential privacy, an adversary is assumed to have a lot of background knowledge. First of all, let individual 1 be the person who's being attacked. About individual 1, the adversary knows that this person comes from either exactly one of two blocks, either say a green block or a red block. And also the adversary knows exactly where every other individual in the table comes from. So here in this example I've shown you, the adversary knows that individuals 2 to n come from some blue block on the map. So the adversary's uncertainty is fully captured by these two input instances. And now differential privacy is guaranteed if any output O cannot distinguish between these two inputs D1 and D2 by a large fraction. That is, the probability that D1 leads to O divided by the probability that D2 leads to O is less than some parameter epsilon which is greater than 1. And if epsilon is larger, then the adversary is able to distinguish between these two a lot, and hence lesser privacy is guaranteed. Okay? Yes?
A clarification question.
Yes.
The probability here is over the choices of the anonymization algorithm, or is it over some private?
The probability is over the choice of the random coins based on the output O. The algorithm that creates the output O, yes. The synthetic data generation algorithm.
So the algorithm must be randomized.
Yes. Actually, it's very easy to see that if the algorithm is not randomized, then given any two inputs, each output will clearly define. You can easily see which input. There always exist two outputs, such that one of those inputs does not create the output that you are seeing here. Therefore, it will breach privacy. So any algorithm that satisfies differential privacy has to be randomized. Okay. So now we use this condition. However, we found that under differential privacy, when we actually did the math and derived the amount of noise that is required, even for small values of epsilon, the amount of noise required was really large. In fact, for epsilon equal to 50, when you had 1 million original workers, we needed 16 billion fake workers on the map, and that totally drowned out the signal. The problem was that there were some outputs which were very unlikely, and these basically caused the amount of noise to be very large. And so we decided to look at a variant called probabilistic differential privacy, which guaranteed differential privacy with a high probability. There were some outputs which appeared a small probability which could breach privacy, but that was okay. And we set delta equal to 10 to the minus 5, and this table here shows you what is the noise required per block that we derived. I'm not going into the math. For 1 million original synthetic workers, this table shows you for various values of epsilon how much noise is required per block. So right now, the current literature stops here and says, okay, add noise to every block on the map. So let's see what happens if you add noise to every block on the map. Let's take this value 0.74. So now there are 8 million blocks on the map, and that's the data sparsity I was talking about. So the total noise, even if I add 0.74 to each block, is around 6 million. So you have 6 million fake workers uniformly distributed on the map. Out of the 6 million, 1 million is going to come from the West Coast, right? And so now in your synthetic data, roughly 1/7 of the points will have residences in the West Coast and working in Washington, D.C., and this is something that you don't want in the output data. Okay, this is bad. But why did we add noise to every block? Why don't we only add noise to those blocks that actually appear in the data? However, we show a theorem wherein that adding noise only to the blocks that appear in the data breaches privacy. And let me give you a quick example of why that happens. So, yes?
Fake workers generated? Are they, so if you're adding a fake worker to a particular block, isn't that the residence has to be in that block?
Yes.
But you're saying that, okay, even for DC, you'll have residences in West Coast.
Yeah, so what you do is, you generate synthetic data independently for each destination. So now look at the destination Washington, DC. Okay? And now the current literature, what it says is add that much amount of noise to every block on the map. Every origin block on the map.
Isn't there a prior on the origin probabilities? Like, okay, everything.
No matter what prior. So the deal is you may have a prior on the origin probabilities, but then the adversary's prior may not match that prior. Right? The adversary knows that you come from one of two blocks, and that prior doesn't match the overall prior because it's sort of, he knows something about you specifically and not the rest of the population. We don't know the adversaries. You have to guard against all kinds of adversarial priors, and that's what differential privacy is doing. Okay?
So what is epsilon here? Can it be 50 to the probability?
Sorry, epsilon here is the amount by which the adversary can distinguish both those two inputs. So epsilon is a parameter. If epsilon is larger, then you get lesser privacy and so on. And I just showed epsilon equal to 50 as some. So basically, if one of them could be 0.01, the other one should be at most. The other probability should be. Yes. Yes, 50 is pretty high. And still you have that bad. But actually, when we were working with the census people, they were like, you give me any epsilon, it's okay. Right now, epsilon is infinity. Okay, so the one property that I'm going to use about the algorithm that I did not fully specify is that if a block P does not appear in the original data, that is, nobody comes from that block, and you don't add any noise to that block, then it won't appear in the synthetic data also. And so we call that such a block to be ignored. So you're going to use this property to show you a privacy breach. So let's say there is a worker W who comes from one of two places, Somerset or Fayette, and then he works in Washington, DC. And you also know that nobody else comes from there. Okay, this is the adversary's prior. So adversary knows that one of these two worlds are possible, right? Wherein in world 1, you know one person comes from Somerset, nobody from Fayette. And in world 2, nobody comes from Somerset and one person comes from Fayette. Now, remember that we are not adding noise to those blocks that don't appear in the map. So in the first case, you will not add any noise to Fayette. So therefore, it won't appear in the synthetic data either. Similarly, in the second case, you won't add noise to Somerset and it won't appear in the synthetic data. But now if you do see a synthetic worker from Somerset in the output data, then you know that world 2 is not possible, and therefore you know exactly where this worker comes from, thus breaching his privacy. Right? Okay. But then in this case, the worker comes from some outlying point with respect to the origin, right? Maybe we can just remove the outliers and still add noise only to the existing points. But then in general, in many cases, especially when the destinations are not in metropolitan areas, half the points coming to the destination were like outlying points. And so removing them completely degraded the utility. So our solution was two-step. First, what we did was we coarsened the domain. And instead of looking at census block, you sort of look at census tracts and so on. But that still reduced the domain size only to like 1 million or so. So the next thing we did was we probabilistically dropped some of the blocks that do not appear in the original data. So we just picked a function based on some external data using some prior knowledge, and then we dropped the blocks that don't appear in the input data with some probability. And we showed this nice privacy utility trade-off theorem, which shows that this parameter epsilon is a parameter of privacy. It basically increases if you drop blocks more aggressively. That is, you disclose more information if you drop these zero support blocks aggressively, and vice versa. So these are the algorithms that we proposed. How do they do with respect to utility? We actually have some theoretical results on how the output data looks like with respect to the input data, how the counts, we actually show that they're bounded by strict ratios. But rather than showing that, I'm going to show you some experimental graphs. So in these experiments, utility is measured by the average commute distance for each destination block, and we compared this metric for the real and the original and the synthetic data. We couldn't use the original data because it's sensitive. Yes, sorry.
So sorry, why is this the right way to measure utility?
This is one way of measuring utility because this is a metric that they really want to have. So in the theoretical results that I talked about, we actually looked at the exact frequencies, and we tried to match those frequencies. But again, that is also may not be the right way of doing it.
Frequencies of what exactly?
Of the origin blocks in the original data and in the published data, and we sort of showed bounds between them. But ideally, what you want to do is create a workload and then say how well you answer those queries on those workloads. Yeah. Any questions? No. Okay. So in the graph that I showed you, I'm going to show you each point is one unique destination block. The blue crosses are the synthetic data and the red pluses are the real data. And the x-axis is the number of workers in that block, and the y-axis is the average commute distance to that block. Okay. Now, for various values, this for one value of epsilon, and this shows that the commute distances are preserved when you're looking at destinations which on an average have short commute distances. So these are destinations which are sort of near metropolitan areas and were in denser parts of the graph, and we are actually doing very well. But however, when you looked at destinations which are in very sparse regions, especially destinations which had very few number of workers going to them, our algorithms were performing very poorly. The commute distance in our synthetic data grossly overestimated the commute distance in the original data. And this is primarily because these are outlying points, and ideally what you want to do when you want to preserve privacy is remove these outlying points, right? So if you really want to guarantee privacy of the outlying points and they're crucial for your analysis, you may have to create new algorithms and model them slightly differently and publish a different data set. Yes?
So how do you, if you're given the anonymized data,
yes,
data with added noise,
mm-hmm.
How do you estimate your query between
yes.
your query is
yes.
average distance?
So
or do you have a formula?
We chose this algorithm because there's a lot of work in the statistical disclosure limitation community on how do you, if you have some statistic, some mean or some variance, what does it look like when you estimate it from the synthetic data? How much bias is there? How much variance is there, and so on. There's a lot of work on that, and we did not do any work towards how do you answer queries based on that, but we're just leveraging whatever work they have. Their estimation accounts for the noise and the sampling process. Yes?
What is the class of queries for which you can show some guarantees on the utility?
So I have not yet studied the class of queries for which I can guarantee the utility. That's what I want to do, but I haven't done that for this. That's what I'm saying, right?
It's a single table aggregation. Right?
Exactly. Yeah. But they look at these average commute distances, average employment, and all those things with respect to, like, spatially. They look at a spatial region and look at what is average employment and so on. And for that, they have done some statistical methods to bound the bias and variance given the amount of noise that is added.
But your example about the adversarial knowledge was looking at point queries, right? Alice or Bob, Alice knows that.
An adversary always looks at a specific person. The whole idea about privacy is the following. You want to specify a privacy about specific properties of individuals. But the kind of utility you want is about aggregate queries on the whole table. Yes?
But here, are there individual identifiers in any case? I mean, the things that are being published are just, okay, this census block has so many individuals.
Yeah. So this background knowledge doesn't appear in the real data, but an adversary may have additional knowledge that doesn't appear in the data, right? That is, you come from some small area on the map. And that's the identifying knowledge that an adversary has. That you don't know. That's what you're trying to model here. Okay? So in summary, what I showed you was a real census application wherein currently security was gotten by obscurity. Yes, sorry.
Census data is relatively static, and all you want to do is the average queries. Why don't they just publish the statistic?
Yeah, that's a very good question actually. So in fact, I looked at what are all the things they look at. They're called quarterly workforce indicators. Oh, sorry. The question is this is static data. So, and usually the kinds of queries that they're asking are, say, some average statistics. Why don't you just publish the average statistics? So, usually what they're looking at are quarterly workforce indicators. which are like average employment. In fact, sometimes they look at multiple data sets across years and say hires, new hire separations, and so on. But then I looked at some other uses wherein, so for example, I think the state of Missouri or something wanted to study, use some cool data mining algorithm to study how the new hire trainee or something like that program can be changed based on the changing statistics. So basically, the point I'm trying to raise is that people want to use data analysis tools which are not only these average statistics. And in order to allow those tools to be run, you want to publish the data which is in a form close to the original data. Otherwise, you have to come up with new algorithms to take these summaries and then use it for these analyses. And people don't want to do that. So if you publish the statistics, you also have to publish a lot of auxiliary algorithms that can take these statistics, sort of recreate the original table that people can reuse their old data analysis tools. So that's
data mining algorithm running on top of your anonymized data. It's very hard to reason about the utility, right?
Yes, that's why. So basically, in the statistical disclosure limitation community, they look at how much the bias is, how much the variance is, if you estimate it based on the synthetic data rather than the original data. No, they have some formulas also, but I don't know if it's empirically tested or theoretical. I mean, some of them have formal guarantees, while others are empirically tested. Yeah, but that's a good question. I mean, there is a whole field of research in the statistical disclosure limitation community. And most of the research is how useful is the output data set with respect to the input data set. Okay. So yeah, I showed you a formal privacy analysis, and in the experimental evaluation, I showed you that possibly it might be useful to publish multiple versions of the data, and so on. Yes, one more question?
You had some variation on differential privacy.
Yes.
This is what your algorithm is based on, right?
Yeah, it guarantees privacy based on the variant of differential privacy rather than the original.
You were mentioning there's some relationship between differential privacy and the diversity that you would highlight.
Is there a relationship between different? No, I mean both of them. So they make very different choices in the space of privacy definitions. The kinds of sensitive information, the kinds of adversarial background knowledge are very different. In some cases, diversity seems to be sufficient. In some other cases, you need a very strong condition like differential privacy.
How much noise did you have to add for your definition of?
I showed you some values, right? Per block, the amount of noise that I had to add. Sorry, that. This is for epsilon delta equal to 10 to the minus 5 and epsilon equal to various values that I showed you. Okay? Okay, let's move on, and then I described to you two things, right? One, how do you formally define privacy? And secondly, and then I showed you a whole space of privacy definitions. And then secondly, I showed you, okay, I mean, when you want to apply to a real application, what are the steps you have to take? And in the case of data sparsity, I showed you some tools of how you could get useful information despite data sparsity. Now I'm going to, in the last 5 minutes, I'm going to quickly show you how to apply this work towards a grand challenge of building a privacy-aware web. I mean, web is the biggest problem, is the place where you have the biggest privacy problems. In order to solve, so the kinds of questions you want to answer are these, right? You want to create these kinds of applications, but then you want to also guarantee privacy. How do you go about doing it? So one way is you have this large pool of user-generated private data, and then you take your real applications, and then analyze privacy and create privacy-preserving variants of those, and then apply them directly to the user-generated private data. However, this approach does not scale because of 3 reasons. First of all, users cannot check whether these algorithms that are using the data are privacy-preserving or not. Secondly, when you analyze the privacy of an algorithm, you take it standalone, look at the privacy of it, but then now you have to run it concurrently with other privacy-preserving and non-privacy-preserving algorithms. So now all bets are off whether it guarantees privacy or not. And finally, you don't want too much burden on the app developers themselves, right? So one of the biggest problems with cryptography is that you have all these cool primitives which have provable guarantees of security, but then these developers come in and use them the wrong way, and then you have no guarantees of security anymore. So rather what I think we should do is, going ahead, we should create this platform that exposes an anonymous view of the data, such that all these web applications can directly use the user-generated private data via this anonymous view without any changes happening, without changing the application code themselves. And in order to do so, there are like many challenges. The first main challenge is that how do you manage this data? You have, on an average, every day you're about 4 terabytes of data, and there are millions of users across the planet. So data is massively distributed, and even if you sort of handle them in a centralized fashion, it's going to be distributed over a large number of data centers. One specific question here is how do you distribute these anonymized algorithms, right? How do you place these, how do you physically store the data so that you can have fast parallelizable anonymous algorithms? The second issue is what tools are needed for data anonymization. So I showed you some tools, but I also showed you that publishing multiple anonymous versions of the data sets improves utility. So the problem of analyzing privacy of multiple releases is in general a hard problem. And right now people don't have good ways to solve this problem. One solution that I've identified that might become very useful is to create what are called composable privacy definitions, wherein it's enough to analyze the privacy of individual anonymizations. So you say that first this one is C1 private, this is C2 private, and so on. And then if they're composable, you have some function which you can apply to these analyses, and you can directly get a privacy analysis of all the multiple releases. Also, I only showed you static data, right? On the web, data is never static. And now once you have updates, you also have privacy problems because of the updates. And adversaries in general right now are passive, that I showed you, right? They just have information about individuals before looking at the data. But now if you have social networks, adversaries can go in, create new links, create subgraphs, and so on, and see how they change in the anonymous data. And so you have to guarantee privacy against all these actively changing adversaries. The third important problem, and this was highlighted by some of the questions, was, okay, you have these multiple anonymous views of the data. How do you learn from these anonymous views? Again, learning from multiple different views of the data is in general a hard problem. And one specific problem is, given an application with some specific information need, and different anonymous views based using different algorithms, how do you pick the best anonymous data set that gives information for that specific application? This is sort of similar to this database problem of information integration if the views are based on SQL queries, right? But now you also have randomized algorithms, and this makes the problem harder. And finally, I mean, this is probably something that's very important. How do users specify their privacy preferences? So right now, the user was not even in the loop in all of my talk, right? And right now, the only way they specify privacy preferences are using opt-ins and opt-outs, where opt-out means don't disclose any of my information. But in general, we also want some sort of opt-partial, which says that, okay, you release this information, but I want to bound the amount of disclosure that is happening. You don't disclose it fully, but you sort of maintain my privacy. And that's the kind of privacy definition that I've showed you in this talk. The question is, will users be able to specify this opt-partial, or can they be incentivized to specify opt-partial? And this is an important question in the field called usable privacy and security community. So putting all of this together, we can now sort of build this system which will actually be a platform for privacy-aware web. And this requires research in privacy, databases, distributed systems, and so on. Today I talked about some of my work in privacy definitions and privacy enforcement. I also worked on peer-to-peer database systems, publish subscribe systems, and also secure distributed computing. And I'll be glad to talk to you about those later on. Thank you, and I'll answer any questions that you have. Yes?
See, you mentioned this probabilistic differential privacy, right?
Yes.
So there you introduce greater than 1 minus delta. It's okay to breach privacy on some specific individuals.
Not specific individuals. There are some so you could create an output with an astronomically low probability that can breach privacy.
So what does that mean?
It means that with a very small probability, you could breach privacy.
Of what? Of certain individuals?
Of a bunch of individuals in your table.
Okay, so
I mean, you raise a very valid point. Maybe it should be a better way to state it is, okay, I guarantee the privacy of most of the individuals in the table, and there's a very small fraction for which I may not guarantee privacy.
And now can you apply the same to your L diversity? I mean,
you could, yes. Yes, and you'll get more useful data in that case. But yeah, we didn't do it. But yes, that's a good point. You could do it. Any other questions?
Okay, let's thank the speaker.
Thank you.